Good evening. I thought that I would go through electrolysis, um, as I've done a lot of questions on it and have had a lot of trouble with it and kind of needed to develop a comprehensive guide with a few others to kind of get the gist of how electrolysis will be on the exam and how we can solve problems with it. So here we have a diagram of an electrolytic cell. Notice there's no salt bridge, and that the aqueous solution is connected between both the anode and cathode. The first thing that is important to remember is that oxidation always occurs at the anode and reduction occurs at the cathode. A good way to remember that is a red cap, i.e. Reduction at the cathode and therefore oxidation at the anode. And so an electrolytic cell is in some ways the opposite of a galvanic cell. In a galvanic cell, the reaction that sends electrons from the anode to the cathode is spontaneous, whereas in an electrolytic cell, obviously, it's non-spontaneous, so power must be added. This means that in an electrolytic cell, the anode is positive and the cathode is negative. Now that's not current, that's polarity. So you have electrons being created here, E minus, and they're going up there, and they're actually attracted over here to the negative. It's its polarity. So the power supply needs to add needs to create the negative polarity for these guys to be to go that way, and then come in here and be reduced at the cathode. So electrons flow the same way from anode to cathode in both galvanic and electrolytic. It's simply the polarity that changes because you need to attract the electrons to the cathode in an electrolytic cell. Okay, so let's say you want to work out what happens in an electrolytic cell. First step, identify the ions which exist in this solution here. Important to note, don't forget about water, because that can react under the standard electropotentials. It's in there twice, I believe. And don't forget about reactive electrodes. For example, if these electrodes are copper, copper can undergo redox reactions, so it might actually react. However, if the anode or cathode is made out of platinum or carbon, then it's considered unreactive. Yes, so first step, identify ions in solution. Next step is to write all possible reactions at each electrode and their standard reduction potentials based on the charge of ions and electrodes. Okay, let's break that down. So each electrode is positive and negative. And you have both positive and negative ions in this solution. And so obviously the positive ions are going to go to the cathode, which is negative, and the negative ions are going to go to the anode, which is positive. And so at the anode, I like to create two kind of areas. So I say anode, and then I list everything that can happen at the anode, and then the cathode. So obviously all of the ions here are going to be positive. Are going to be negative because the anode is positive. So all of the ions here are going to be negative, whereas at the cathode, because it's negative, all the ions reacting here are positive. And so once you have your lists, remembering water and electrodes that might be reactive, then you move on to step 3. And step 3 states that the reaction with the most positive reduction potential will occur at the cathode, and the most negative reduction potential will occur at the anode. So you have the anode here, and typically it's written as reduction. So a particular ion here is reduced, let's say, with 2 electrons, and it goes to whatever it is, let's say is a solid, right? and that'll have a reduction potential of, let's give it 0.79. And then down here, similarly, you might have a thing B. Let's just rub that out a little. One of your reactions might be B plus 2E minus goes to, I don't know, B solid, right? And that's how it's given to you in the standard potentials. And so you would look at the anode and you'd say, let's say that has plus 0.79, and let's say you have another thing at the anode, which is, so it's meant to be a C there, and let's say that has 0.81. Now at the anode, what's occurring is oxidation, not reduction, so you actually need to reverse these, and that means that the standard potentials would become negative, and that would mean that the reaction with the most negative potential when flipped doesn't want to occur. It's a very good rule of thumb. If you have a reaction going this way, A plus 2E minus goes to A, and let's say that has a reduction of 0.81. That wants to occur relatively. For example, these are different B's and A's. That wants to occur more than this reaction here. So the more positive, the more it wants to occur, and that one's lesser, so it wants to occur less. So at the anode, oxidation is occurring, so we must flip these equations that you've listed for the anode, and that would, say, for example, become negative, that would become negative, and since the second one, A, is less negative, it will want to occur, and so if it's out of A and C, A will occur at the anode because its standard potential is less negative. Okay, and then at the cathode, it's an easier story. Let's say this. Let's say you have D here, 20 minus, D solid. Let's say this guy has a potential of 0.5. This guy has a potential of -1. Then this guy here is going to occur because it's more positive. And so taking into that flipping at the anode because it's oxidation, and not flipping at the cathode, and taking into account our rule that the most positive potential will want to occur, and you need, when you're flipping it, change the sign of the potential, we come to the third rule as stated. The reaction with the most positive reduction potential will occur at the cathode, as we see here, and the most negative will occur at the anode, because you see the 0.8, when it flipped, it became more negative than the 0.71 over here. So originally we had this guy as these two guys as positive, and so when we apply number 3 over here, we can see that A would occur as was shown. Okay, now so we have A happening, B happening, and so when we combine these, we have A over here, and remember it's oxidation, so it's going the other way. Plus 2E minus over here, and we also have B plus 2E minus being reduced at the cathode, goes to B, and we can combine these as usual, and so we get A. Let's say this guy's aqueous. So this guy's aqueous, and this guy's solid. Then we have A solid plus B aqueous goes to A aqueous, B solid. And then, as with the balancing half reactions, that can become more complicated. So, those are the 4 steps. Identify the ions in solution, don't forget about water, don't forget about reactive electrodes. Then, write all possible reactions at each electrode and their standard reduction potentials, which are these numbers here, based on the charge of ions and electrodes, remembering that negative will be attracted to the anode, positive will be attracted to the cathode. Then number 3, the reaction with the most positive reduction potential will occur at the cathode, and the most negative will occur at the anode. And then after that, you can combine the two reactions that you've seen, and you cancel species, and you get this lovely equation down here. Beautiful. So let's do an example, and this is the one prescribed by the syllabus. Okay, we have here the electrolysis. Let me see if I can zoom in. Okay, electrolysis of a 1 molar solution of copper 2 sulfate using copper electrodes with water present. Okay, and so the following species could react in this solution. We have H2O, can be oxidized or reduced. We have Cu2 plus ions in solution, could be reduced, and we have the Cu metal in the electrodes, could be oxidized. So we've listed out here that H2O is actually H3PO plus and OH minus. Those are the two ions there. Now, an interesting thing you might be saying, copper sulfate, that's CuSO4. Why doesn't the sulfate ion want to do anything? Well, that's because the sulfate is actually in its highest state, and so it won't react. It's a spectator ion. Okay, so cool. This is the process. Now I've kind of given away what's going to happen, but you have the copper anode, which is positive, and the copper cathode is negative. And remember, red cathode is reduction, anode is oxidation. And so now let's keep on with the process outlined, and let's look at the cathode. Two reduction reactions can occur at the cathode. We have H2O might be reduced, producing hydrogen gas, and OH minus, and that has a potential of negative 0.83. Or Cu2 plus could be reduced, forming Cu solid, and that has a potential of 0.34. Now, because that wants to occur more, because it has a higher potential, that's what's going to occur. And so that's what you get. At the anode, another two oxidation reactions can occur. We have here Cu2 plus here with a potential of 0.34, and we have oxygen here being happening here, and that gives you a potential of 1.23. Now here you might be thinking, oh, those look like reduction equations to me, and you would be exactly right. However, when we flip them, obviously we flip the sign on these potentials, and that will give us the notion that the first equation will happen as oxidation because it'll have negative 0.34, whether the other one will have negative 1.23, and the more positive, when flipped, wants to occur. So, kind of a shortcut here, since CuS has a less positive E in this state, in this writing it out as a reduction equation, it will undergo oxidation. And so we have there the two equations. That's reduction here, and then oxidation here. Cool. Beautiful. The only other nuance to be considering about is combining these two equations, and so that would be Cu2 plus aqueous plus Cus goes to Cus plus, but it doesn't really make sense in this situation. It will, however, make sense with hydrogen fuel cells. And lastly, at non-standard concentrations and other concentrations, the actual reactions may differ because these values here, they're standard potentials. So at different concentrations, at different temperatures, at different pressures, alternative potentials occur, and so you can't necessarily use this process. So if they ask in the exam, what are the limitations of these predictions, you can say that. So I hope that cleared up electrolytic cells. Again, just one recap. In electrolytic cells, the anode is positive, the cathode is negative. Oxidation always occurs at the anode, reduction always occurs at the cathode, just as in a galvanic cell. And when you want to identify what's happening in an electrolytic cell, you identify the ions in solution, you write all possible reactions at each electrode and their standard reduction potentials based on the charge of ions and electrodes. Then the reaction with the most positive reduction potential will occur at the cathode, and the most negative will occur at the anode. And then you combine the two reactions and cancel species if it's useful to do so. Have a nice day.